Hi, I'm Steve D'Antonio, and I'm in the engine room of a 63-foot motor yacht currently anchored in Portage Bay, Alaska. Today I'm going to talk a little bit about the charging system on this vessel, specifically alternators, regulator, battery charger, inverters, and battery bank. In a previous presentation, I concentrated specifically on the alternators. This time we're going to cover the whole system. So let's look at what we have here. On this vessel we've got twin high output alternators, each one of which is capable of putting out 175 amps. Then we have a voltage regulator that controls the field on these alternators and controls their output simultaneously. So in this case, both of these alternators are parallel. Their output is both going to the house battery bank. That's an ideal way to set this system up. If you have a large battery bank, you want to use all the charging capability at hand to recharge the bank that needs it the most, which invariably is the house bank. The challenge there is to make sure that both of those alternators work in a fashion that's complementary to each other rather than fighting each other. If they're independent and each uses its own regulator, then you can have a situation where one of them essentially shuts off, which we don't want, of course. So in this case, we're using a single regulator that's designed to control two alternators at the same time, and it is wired to both of these alternators, and therefore they behave essentially like one large alternator. And that's really advantageous because, again, we have the bulk of our charging going to the bank that needs it the most, the house battery bank. That's the one that's, for the most part, being discharged the most heavily. Start batteries we don't worry so much about because we use so little of the power from those. But with the house bank, we want maximum charge capability. So again, this system, very rugged, bulletproof design, alternators that are designed to run at high output for long periods of time because they're capable of dissipating heat very well. So purpose made for this type of approach. The regulator that we're using in this case, again, a very rugged, heavy-duty unit that's designed to control both alternators simultaneously. There are some other features on this alternator that are worth pointing out, one of which is this temperature probe. This enables the operator of the vessel to monitor the case temperature of the alternator while the vessel is underway without having to come down here and shoot it with an infrared pyrometer. So we know if an alternator is overheating or running hotter than normal, we can pay more attention to it. So that's a nice feature to have, an add-on feature. You can see that the cabling is very heavy duty, very rugged and well supported. It has additional insulation on it with this loom material, so no chance of chafe. You'll also notice that the output studs, the positive output studs, have a rubber boot over them that completely covers the stud on this alternator. That's very important because if something were to contact that stud, a piece of metal for instance, we could end up with a short circuit. So we're very sensitive to insulation on high output charging systems, especially because we've got lots of current here and very large cabling, and in the event of a short circuit we would generate a lot of heat and potentially a fire. So we've got to be very careful about things like that. So again, the backs of both of these alternators are supporting wires that are very well insulated and again very well supported. They can't jiggle around or chafe or be damaged by the vibration from the engine. Alright, so next stop is going to be aft. We're going to go take a look at battery charger, inverter, and battery bank. Okay, we're in the lazarette now of this vessel, and we're going to look at inverters, battery charger, and battery bank. You can hear a fan running in the background, and that's because this is an operating vessel that's at anchor, and the inverters are supplying all of the AC power for the boat right now. So there's someone in the galley cooking, and she's using the stovetop, and that is running off of these inverters. This inverter bank of two inverters is capable of delivering 240 or 120 volts. So a very capable system that can run many of the AC components on the boat without having to run a generator, including stove and other components. So that's why these fans are running right now. These are working. So we have inverters that are capable of inverting, which they're doing right now. That is converting battery power into AC or shore power type electricity, or the same kind of electricity you'd get from a generator without running any of that gear. They're converting battery power to AC power. They are also capable of charging batteries, essentially running in reverse. When you apply AC power to them, they then put out DC power at the voltage that the batteries operate at, 24 volts in this case, and provide charge to the batteries. So a very versatile component. And today you'll find inverters on many boats for just this reason. They're capable of doing quite a bit. And not only do they invert, but they're actually very good battery chargers in many cases. They provide batteries with a multi-step charge, and that is the healthiest or best kind of charge for a battery bank. And they are temperature compensated, which means there are probes on these batteries that are measuring the temperature of the case of the battery, and then relaying that information to the inverter charger through this data cable, and the inverter charger is then tailoring that charge for the batteries based on their temperature, because warmer batteries must take a slower charge or a lower voltage charge than batteries that are cool. So in the climate that we're in now, where it's 53 or 55 degrees outside and the lazarette is rather cool, these batteries can charge more quickly than they could if, say, we were in the Bahamas or Baja, where they'd be hot. So the charger would essentially ratchet back the charge because it knows the temperature of the batteries. That approach is very good and very important because it extends the life of the batteries. Not only does it enable you to charge batteries more quicker when they're cool, but it ensures that the batteries last as long as possible because we're charging them in a manner that is appropriate based on their temperature. So a lot of good things about inverter chargers. They're very smart today. Most of the inverter chargers that we see installed on yachts like this, they do a good job of charging batteries. But it's not the only charge mechanism that we have. We have a standalone battery charger, in this case a 100 amp, 24 volt charger that does nothing but charge batteries. It is not an inverter, it does not create AC power. All it does is produce 24 volts DC for the batteries to charge them when it's supplied with AC power, which can come from either shore power or one of the vessel's two generators in this case. Why have two? Well, we have redundancy, so that if we have a failure in either one of these, we still have a way of charging batteries. In fact, on this vessel we have triple redundancy because we have alternators that charge the batteries, inverter charger, and standalone battery charger. But that's not overkill because, again, for an expedition type vessel that's traveling far from help essentially and far from parts, you want to have additional redundancy for critical systems like the battery and DC system, because without this, the vessel's essentially dead. If you have no house battery power, you can't run anything on the boat. So to have a system like this with essentially three different charge sources, alternators, inverter charger, standalone battery charger, is not a bad idea. I endorse that wholeheartedly. The other component in this system is the batteries themselves. This is one of 4 battery banks on this vessel, all of which are parallel together for ordinary operating conditions. They can be isolated if necessary. If there was a failure in a single battery, that battery bank could be taken offline with a battery switch that's on the battery switch panel, which is also located in this lazarette. The batteries are, as I said a little while ago, the heart of the DC electrical system. It's what enables us right now to be operating this whole vessel, including the galley, with no generator operating while we're at anchor. Power is being supplied from these batteries, in this case through these inverters. They're also supplying direct DC power to all of the DC components, lights, instruments, anchor alarm, and things of that sort. Anchor light, all of those are running off this fairly large DC house bank. DC battery banks, or battery banks rather, should be designed in such a way that they match the charge capability, meaning that in order to recharge this bank, we would run the engine or generator powering inverter charger or charger for a reasonable amount of time. If the battery bank is too big for the charge source, we can end up with a situation where we can't reasonably recharge them, or we can't recharge them in a reasonable amount of time. That's something we want to avoid. That's an equation that must be calculated by folks who know how to do that rather than just winging it. You want to make sure that your charge capacity matches your battery capacity, and your battery capacity needs to match or be designed to supply the loads of the vessel for the length of time that you want to use the battery. So for instance, if we want to run this vessel for 12 hours without starting a generator or the engine, then the battery bank has to be sized so that it can provide enough power to operate all of the systems that we anticipate running: lights, refrigeration, freezer, galley. All of those things need to be calculated. Then we need to size our battery bank so that it will run all of that, all of those components for the 12 hours that we want without exceeding 50% of the battery's capacity. 50% is the magic number. We don't want to go below that 50% number for a variety of reasons, but the two most important being we'll get the most life out of the batteries, the most number of cycles, and the most number of amp hours during the life of the battery out of that battery bank if we don't exceed that 50% number. And if we discharge the batteries beyond 50%, we're stressing them in a way that makes them more likely to fail, to have a plate failure or some other internal component failure. So that 50% number is very important. So when the calculation is being done to determine the size of the battery bank, we want to make sure that we're paying attention to that 50% as our usable capacity of the battery bank, and that we don't exceed that 50% number when we're using power out of the bank, essentially. And then again, we want to make sure we can put that power back in a reasonable amount of time by having a large enough charge or large enough charge capability and or large enough alternator output capability so that those batteries get recharged without us having to run either of those for too long.